Hello and welcome. My name is Noah Deere, and this is Lesson 13 of the Math 254 Vector Calculus sequence at PCC. Today we're doing double integrals over rectangles. So we're going to be looking for the volume of the space under a surface given by a function in two variables. And before we do that and get into it, we're going to do some review of how we found areas under curves for a function in a single variable. And we're going to build up just like we did in second term calculus, so in integral calculus, how we built up a Riemann sum in order to find the area under a curve. We're going to build up a double Riemann sum in order to find the volume under a surface. Then we're going to look at a midpoint rule for approximating volumes given data, and we're going to look at finding the average value, the average height of a surface given some region. Oops. Come on. There we go. All right. Section 13.1, definite integral review. In single variable integral calculus, the definite integral is defined to be the area between a curve and the horizontal axis. And we can have negative area too, so if we're below the x-axis, then we consider that negative area. And if we wanted to find it as a positive area, we would just negate it and work with it that way. But given a function y equals f of x, the area from x equals a to x equals b under the curve can be found by cutting up the interval a comma b into n subintervals, constructing a rectangle for each subinterval whose width is that of the subinterval and whose height is some y value of the curve within the subinterval. Let's take a look at the graph so we can see what's going on here. So here we have a curve, y equals f of x. We have some interval from 2 to 5, that's my a and my b. And then we cut it up into n subrectangles. And the width of each rectangle is the total width, 5 minus 2 divided by how many rectangles we have. So right now I have 11, so it would be 5 minus 2 is 3 over 11th. 11 is 3/11ths is the width of a rectangle. Then we set the height of each rectangle. Here we're using left end points, so I have the left end point of each rectangle touching the curve, and then we add up the areas of all of these rectangles to get the total area under the curve. And so that looks like 6.0375 here. Oh, so that's the actual area, and this is using an integral in GeoGebra, and here we're doing the rectangles. The sum of their areas is 5.47, so it's a bit of an underestimate there. As we increase the number of rectangles, we see that underestimates should be getting a little bit better. Now we have the sum of my rectangles is 5.805, which is definitely closer to that integral. Let's take this all the way up to 50, and we see that we're only 0.1 beneath now. So that's what we're doing in practice. We're going to use this Riemann sum down here. Let me finish reading this paragraph. Where was I? Then to obtain the exact area under the curve, we take the limit as n goes to infinity. So we're just saying the number of rectangles we want is an infinite number, so that we've constructed an infinite number of rectangles of infinitesimal width. I should be specific here, infinitesimal width, comma, and heights that match every y value of the curve, so that their sum is the area, is the, sorry, I did not have a chance to go through this in detail before reading it. Then to obtain the exact area under the curve, we take the limit as n goes to infinity, so that we have constructed an infinite number of rectangles of infinitesimal width and heights that match every y value of the curve, so that the sum of their areas is the exact area under the curve. This can be done by choosing the widths of the subintervals to be all different and to choose the heights of the rectangles to be any y value within the subinterval of the curve. Let me kind of show you what I'm saying there. Let's drop this number back down. So I could actually make it so that these rectangles weren't of the same width. I could have one that's width is like 1, and one is 1/2, and one is 1/4, and the next one's 1 again, and then one's 3/4, and that's fine. And then the y values don't have to be left end points. They could be midpoints, or they could be 3/4 points, or some of them could be left end points, some could be right. Because as we take the limit as n goes to infinity, it squeezes everything down so that all of the widths go to 0 anyways, and all of the points between. So if I have a rectangle of width 1/2, then I could pick an x value anywhere between 2 and say 2.5 here, and as to plug into my function to get the y value of this rectangle. But as the width goes down, that choice becomes just the single x value of each of the rectangles as their width goes to 0. So whether we're doing left endpoints or right endpoints or midpoints doesn't really matter when we take the limit as n goes to infinity. Where was I? So what I was saying, this can be done by choosing the widths of the subintervals to be all different, and to choose the heights of the rectangles to be any y value within the subinterval on the curve. And moreover, we could find our area with trapezoids instead of rectangles. So there's lots of flexibility in how we can construct these areas. However, a simple way of constructing this is to cut the interval from a to b into n subintervals. A equals x0, comma x1, comma x1 to x2, comma x2 to x3, comma etc., comma x sub n minus 1, comma x sub n, so that we have n subintervals of equal width. Delta x equals b minus a over n, right? So simply making it so that each of the widths is the same. And we can thus find or choose x sub I equals x0 plus delta x times I for I equals 0 to n. So if I is 0, we would just get x0, our left endpoint of the interval. If I is n, we have then multiplied delta x n times and added that to x0, which will give us x sub n. We can then choose the height of the subrectangles for each subinterval to be that of the y value on the curve that is on the left endpoint of the interval, so that the height h sub I equals f of x sub I are the heights of the rectangles 0 through n minus 1. So we're going to not use the n value here if we're doing left endpoints. If we were doing right endpoints, we would choose I equals 1 to n for my x sub I. So the x sub I are the x's that we're plugging into the function to get the y values, the heights of each rectangle. So the area under the curve can in this way be found to be the integral from a to b of f of x dx. This is defined to be the area under the curve of f from a to b. This equals the limit as n goes to infinity of the sum of I equals 0 to n of f of x sub I times delta x. And I totally have a typo. I just said it, and this needs to be n minus 1 if we're doing left endpoints. Taking notes for mistakes to fix for you guys. Where delta x equals b minus a over n, and x sub I equals a plus I times delta x for I equals 0, comma 1, all the way to n minus 1. So let's do an example of this, get it all set up and everything. Find the area under the curve f of x equals 1/2 x plus 3 over the interval from 0 to 4 via the Riemann sum as described above. So we want the integral from 0 to 4 of 1/2 x plus 3 dx. And yes, we could totally use our antiderivative rules in the fundamental theorem of calculus to evaluate this, but we're going to do it using this limit of the rectangles, limit of the area of the rectangles, to rehash the Riemann sum so that we can then apply this for our volumes. So this equals the limit as n goes to infinity of the sum of I equals 0 to n minus 1 of, okay, so f of x is 1/2 x plus 3. So I need 1/2 of x sub I plus 3 times delta x. Now, have x naught equals 0, delta x equals 4 minus 0 over n equals 4 over n. And so x sub I is going to equal 0 plus 4 over n times I. And we'll do from I is 0 to n minus 1 to give us the x values on the left endpoints of our rectangle. So this equals the limit as n goes to infinity. So just think of this as a substitution thing. We have our formula, the sum of I equals 0 to n minus 1 of f of x sub I times delta x, and we just need to plug in now into f x sub I, and we need to plug in for delta x what we come up with for delta x. So the limit as n goes to infinity of the sum of I equals 0 to n minus 1 of 1/2 times 4 over n times I plus 3 times 4 over n. So we'll just go ahead and distribute some stuff across here. I equals 0 to n minus 1 of, when I multiply this in, so I'd have 2 over n times I, but multiply it by this, and we get 8 over n squared times I plus 12 over n. So this equals the limit as n goes to infinity of, so I'm going to do each of these individually. The 8 over n squared, this is actually a constant for the sum, but the n is a variable for the limit. So as far as the sum is concerned, the I is the variable and the n is the constant. N minus 1 is actually a constant. It's the final, it's how many terms we're using. We're using n terms because we start at 0, so 0 to n minus 1 is n terms. And n is some constant that we've chosen. It could be that we've cut it up into 4 rectangles, 6 rectangles, 8 rectangles, what have you. We'll take the limit after taking the sum here. So this is 8 over n squared. And we need to remember that the sum from I equals 0 to n minus 1 of I, this equals n minus 1 times n over 2. So when I take the sum of I over and over again, really this is a constant, so it can be thought of as factoring it out of the sum, and we're just adding the numbers 0 plus 1 plus 2 plus 3 plus 4 plus 5, adding all of those up and then multiplying by 8 over n squared. When we add all of those up, this is what we get, is what however many numbers we're adding to is n minus 1 times n over 2. Plus, now the sum of 12 over n. Well, the sum of any constant is saying that I'm adding this to itself n times. So this is c times n. So the sum of 12 over n is saying we're just adding this. I is not in this, so I is our variable. There's no I, so this is just saying add this constant to itself. Here we're saying add this constant times 0 plus this constant times 1 plus this constant times 2 plus this constant times 3, etc. Here it's just this constant plus this constant plus this constant, and we're doing it n times total, so that's 12 over n times n, which we're going to obviously simplify this. I think I can do this in just a couple more lines here. This is the limit as n goes to infinity of, here I'm going to get, well, let's write this out. This is 8n squared minus 8n over 2n squared plus 12 equals 4 plus 12 equals 16. And I'm getting the 4 here from 8 over 2. The limit as n goes to infinity of this fraction is simply just the ratio of the highest degree terms. So 8 over 2 is 4, plus the 12 sticks around, we get a total of 16. Let's take a look and make sure that that makes sense here. If I was doing this using integration, we would get 1/2 times 1/2 x squared plus 3x from 0 to 4 would equal 1/4 times 16 plus 12 minus 0 when I plug in 0. And sure enough, we get 4 plus 12 equals 16. So we have confirmation here. Great. So that is our quick review of doing Riemann sums with functions in a single variable. And now we will move on to doing it with functions in 2 variables. So hold on to your hats and glasses. We're going to have a lot of little tedious stuff, but we'll get through it. 1 second. All right, section 13.2, volume, double integrals, and Riemann sums. We can now extend this idea to functions of 2 variables to find the volume between the xy plane and a surface given by z equals f of x comma y. Let the region R equals a comma b crossed with c comma d. So this is an x interval and this is a y interval. Represent the set of x comma y such that a is less than or equal to x is less than or equal to b, comma c is less than or equal to y is less than or equal to d. So define f of x comma y on R, this region that we're talking about, this rectangular region, and for the moment assume that f of x comma y is greater than or equal to 0. As we saw with taking the integral or looking for the area under a curve for a function in a single variable, if we had area underneath the curve, we would have it be considered negative area. We will eventually do the same thing here when we're taking the integrals for functions in 2 variables. But for now, as we do this discussion on how we set up the Riemann sum, we want to just assume that everything's above 0 to be able to talk about how it sets up. So we're going to subdivide the x interval from a to b into n subintervals, x0, x1, then x1, x2, all the way down to x sub n minus 1, x sub n. And then we'll take the y interval c comma d, and we're going to cut it into m subintervals, y0 to y1, y1 to y2, etc., all the way down to y sub m minus 1, y sub m. To obtain the rectangles, r sub I comma j equals x sub I comma x sub I plus 1 crossed with y sub j comma y sub j plus 1. So this is a rectangle that we're going to look at here where this point is x sub I, y sub j, and this is x sub I plus 1, y sub j plus 1 in the upper right hand corner. So this is considered rectangle r sub I comma j, and this we have these rectangles for I equals 0, 1, 2, all the way up to n minus 1, and j equals 0, 1, 2, all the way up to m minus 1, so that we're doing lower left end points for these rectangles. We'll see that in the picture here in a few moments. Note that we could construct the rectangles to not be of uniform widths and still have this work out, but for simplicity we will construct them to all have equal widths so that delta x equals b minus a over n, and equal lengths, delta y equals d minus c over m. Remember, n is the number of cuts that we do in the x direction, or it's the number of intervals that we have in the x direction. There's actually one less cut than that. And m is the number of intervals we have in the y direction. So this is going to give n times m rectangles of equal width and length. So let's take a look at this graph now. Here's from a nice view. If I look from the top view, so I've got a region here I'm not seeing my axes. I don't know why it's not showing the axes. It's weird when I try and do this in this small window. But this function set up where x is going from 0 to 3. We have it cut up into 6 subintervals, each of length 1/2. So 1/2, 1, 1.5, 2, 2.5, 3. And there's a wide interval of total of 2. So again, these are cut into widths of 1/2, 1, 1.5, 2. So 4 intervals in the y direction, 6 in the x direction. So this is saying n is 6 and m is 4 as I have it now. So what we can see, what we're going to do here is as we cut up this region into these rectangles, then we can get the volume of each of these prisms here, these rectangular solids, by multiplying their width times their height, or their width times their length times their height, and choosing their height. What we're going to do initially here is use these bottom left endpoints so that the height of this rectangular solid matches, well, really the height of each rectangular solid matches the z value on the surface when looking at the lower left corner of the rectangles that we've cut the region into. And then we can add up the volumes of all of these rectangular solids, and that gives us an approximation to the volume under the surface. And then we can take the limit as the number of rectangles goes to infinity by cutting this into smaller and smaller widths in both the x direction and the y direction. So we can then inscribe a rectangular solid on each subrectangle whose widths and lengths are all delta x and delta y respectively, and whose heights are h sub I comma j equals f of x sub I star comma y sub j star, where the point x sub I star comma y sub j star is any point in the interval x sub I comma x sub I plus 1 crossed with y sub j comma y sub j plus 1. That is that rectangular region. This is r sub I comma j. As long as we're in that rectangular region, we plug any point in that rectangular region into the function to get a height there. And again, like I said, we're going to start by assuming that we choose x sub I star comma y sub j star to equal, let me write this down, 4 lower left corners. We choose x sub I star comma y sub j star to equal x sub I comma y sub j. If we wanted to do, say, lower right corners, we would choose x sub I star comma y sub j star to equal x sub I plus 1 comma y sub j. So we're still doing the lower, but we're now doing the right corners by having x go over to the I plus 1 position. So for sample points x sub I star and y sub j star, we define the double integral over the region R to be the volume of the solid between R and the xy plane, and this should be volume of the solid between R in the xy plane and f of x comma y. So the volume equals the double integral over the region of f of x comma y delta capital A, where A, well, let's say dA equals dx dy. This is the instantaneous change in the area. This is the instantaneous change in x times the instantaneous change in y, so that's the instantaneous change in the area. So here this equals the limit as m comma n goes to infinity. That's the number of subintervals in the x and y direction. So we're making that number go to infinity for both. And we're summing, we have this double sum. We're summing from I equals 0 to n minus 1 and j equals 0 to m minus 1 for f of x sub I star comma y sub j star times delta x times delta y. So this is the width of the rectangle. This is the length. And this is the height. And we're doing this, we're summing over all of the, j is the lengths, and I is the widths. So we're summing over all of these widths and all of the possible x values and all of the possible y values for all of the possible rectangles, right? So, and I mentioned that a second ago, where dA is the infinitesimal area of the rectangles dx, dy. So later in this lesson, we're going to look at choosing x sub I star, y sub j star to be the midpoints of the rectangles, r sub I, comma j. But for now, we will choose x sub I star, comma y sub j star to be the lower left points of each rectangle, so that x sub I star equals x sub I equals x naught plus delta x times I, and y sub j star equals y sub j equals y naught plus delta y times j for I equals 0 through, it should be, well, we can choose 0 through n and j equals 0 through m, but if we want the lower left, we want to make this n minus 1 and this m minus 1. Okay, so we've done a lot of talking theory on how to set this up. Let's put this in practice. Let's look at example 13.2.1. All right, I'm going to try and go slow here. There's a lot of little tedium in algebra that we have to be paying attention to. This first one's not going to be too horrible. Note, I'm having both of these first two be examples. The first one's not too bad. So here we have, let's start with, we want the volume, which equals the double integral over the region, given here. This we could also write as -2, 2 times 1, 6. And here we have 4dA. This equals the limit as m and n go to infinity of the sum of I equals 0 to n minus 1, j equals 0 to m minus 1 of f of x sub I, y sub I, or y sub j rather, times delta x, delta y. So we need expressions for x sub I, y sub j, delta x, delta y, and we need, so my function here, we have f of x sub I, y sub j equals 4, and we have delta x, so the total width of the x is 4, and we're cutting that into n subintervals. Delta y equals, total width is 5, we're cutting that into m subintervals. And so we have the limit as m and n go to infinity of the sum of I equals 0 to n minus 1, the sum from j equals 0 to m minus 1 of 4 times 4 over n times 5 over m. And this is a simple situation where we could find this volume by just recognizing that this is a rectangular solid, which we'll do in a second to confirm. But it's nice to start with a simple example for the purposes of just seeing how to set up this double Riemann sum. So the limit as m and n go to infinity of a double sum I equals 0 to n minus 1, sum from j equals 0 to m minus 1. And this is 2080 over n times m. So we're going to essentially, we think of this as a sum and then a sum of the sum. So this sum is m instances of this happening over and over to itself. So again, the sum, or I'm going to put this, the sum from j equals 0 to m minus 1 of some constant. This equals the constant times m, because from 0 to m minus 1 is m occurrences. I guess I could even write this out. This is c plus c plus c over and over plus c m times equals c times m. So this equals the limit. So m comma n goes to infinity of the sum of I equals 0 to n minus 1 of 80 over n times m. These m's will cancel. And then when we take the sum, well, let's go ahead and write that this equals the limit as m comma n go to infinity of the sum of I equals 0 to n minus 1 of 80 over n. And if I add 80 over n to itself, this is n times, then we're just going to get 80. And now we have no variable left. I mean, this is technically over n times n, but these cancel, and the limit of a constant is just itself. So we get 80. And we can also confirm this because the volume is the width times the length times the height. The width in the x direction is 4. The length in the y direction is 5. The height in the z direction is a constant 4 here. And so we get 5 times 4 is 20, times 4 is 80. So we're confirming that way. Excellent. Okay, if you were struggling at all with that last example, go through, rewatch it, make sure you're understanding how to put it together completely, because now we're going to jump into one where everything gets a lot more tedious. There's a lot more details to this next one. The z value is no longer just a constant 4. It is now varying with x and y. So my z value is going to be x plus 2y squared. So we're going to have a lot more little things that we have to worry about as we get through this. But the setup's going to start out the same. So we have the volume is the double integral over some region of f of x sub I y sub j times delta x, whoops, no, right now I want to say dA, and this equals the limit as mn goes to infinity of the double sum from I equals 0 to n minus 1, the sum of j equals 0 to m minus 1 of f of x sub I y sub j delta x delta y. So we need to find x sub I, y sub j, delta x, delta y. Excuse me. So we have delta x, where was it? Delta x equals, total width is 2 over n subintervals. So then x sub I equals x naught plus delta x times I. So in our case, this is going to be 0 plus 2 over n times I equals 2 over n times I. Now our delta y, this equals, total width in the y direction is 4 over m subintervals. So y sub j equals y naught plus delta y times j. So this is going to be 0 plus 4 over m times j, which simplifies to 4 over m times j. Now my function is x plus 2y squared. So f of x comma y equals x plus 2y squared. So f of x sub I, y sub j is going to be 2 over n times I plus 2 parentheses 4 over m j squared. And I'll write this as 2 over n times I plus 4 squared is 16 times 2 is 32 over m squared times j squared. So now we can start plugging all of this together. My limit as m and n go to infinity of the sum from I equals 0 to n minus 1, the sum of j equals 0 to m minus 1 of So now I can plug in for f of x sub I, y sub j, this expression that we just found of 2 over n I plus 32 over m squared j squared. And delta x is 2 over n, delta y is 4 over m. So here we have the limit as m and n go to infinity of the sum of I equals 0 to n minus 1, the sum of j equals 0 to m minus 1 of, now we distribute this in, so we get 2 times 4 is 8 times 2 is 16 over n squared m times I plus 32 times 2 is 64 times 4 is 256 over n times m cubed j squared. And we're going to keep in mind that we're going to do the inner sum first, the right sum first, right? So here I'm taking the sum of this. Now for this sum, j is the variable, so 16 over n squared m times I. All of this is considered a constant, so we're just doing this m times. I'm going to write this out. If I have the sum from j equals 0 to m minus 1 of some constant, as far as this sum is concerned, this is c plus c over and over again, specifically m times. So this equals c times m. So this is 16 over n squared m I times m plus. Now in the second term, the 256 over n times m cubed is a constant, but the j squared is not, because we're summing over j. J equals 0 to m minus 1. So we need a formula for this. Now, normally the sum from j equals 1 to m would be given by m times m plus 1 times 2m plus 1 over 6. And so if we do the adjustment that we're doing from j equals 0 to m minus 1, this is going to be given by m minus 1 times m times 2 times m minus 1 in parentheses plus 1 over 6, and this simplifies down. Oh, I am totally making a little mistake here. I need to adjust. Move this over. Move this over. This over. we're not taking the sum of this, and this is really important. The sum of j squared equals this. The sum of j squared equals, so the sum from j equals 0 to m minus 1 of j squared equals m minus 1 times m times 2 times m minus 1 plus 1 all over 6. So this equals m times m minus 1 times 2m minus 1 here, 2m minus 1. The 2 distributes to get a minus 2 plus 1 is a minus 1 all over 6. So keep in mind, we are not summing the m minus 1 times m times 2m minus 1 plus 1 over 6. We are summing j squared and getting this expression out. So this equals the limit. M and n are going to infinity after we finish taking the sums. The sum here from I equals 0 to n minus 1 of 16 over n squared m. Actually, the m's cancel here, right? Might as well do that now. Plus 256 over n times m cubed times m minus 1 times 2m minus 1 over 6. And we are going to take the sum of all of this now. So we get this equals the limit as m and n go to infinity. Now here, this is the 16 over n squared is a constant because here the sum is in I. So we're taking the sum of I. So I'll pull the 16 over n squared out. We have the sum from I equals 0 to n minus 1 of I, plus the sum of from I equals 0 to n minus 1. Let's reduce this a little bit. This is going to be 64 over 3n times m cubed times, it's going to be 2m cubed. Let's do this over here. So we're going to have m squared minus m times 2m minus 1 all over 6. This equals, I'm going to scroll down a little bit here. This equals 2m cubed minus m squared minus 2m squared is minus 3m squared. And then we'll have our minus m term here. And then no constants all over 6. So we can bring that over. 2m cubed minus 3m squared minus m all over. Oh, we already have the 6 we used to reduce, so that's now a 1. So this equals the limit as m and n go to infinity of 16 over n squared times. Now the sum from I equals 0 to n minus 1 of I, this equals n minus 1 times n over 2. And so we can plug that in for the sum of I. Plus, over here, we have, now this is going to be, I'm just going to copy this for a second, 64 over 3n times m cubed times 2m cubed minus 3m squared minus m all over 1 times n. And that's because this doesn't have any i's in it. So this is considered a constant as far as this sum is concerned. So this is just this whole thing added to itself a total of n times. And we're just about home free here. This is the limit as m and n go to infinity of 8n squared minus 8n over n squared plus, here the n's are going to cancel, so we get 128 m cubed minus 3 times 64 is 192 m squared minus 64m all over 3m cubed. Now as n goes to infinity, this just goes to 8. As m goes to infinity, this goes to 128 over 3. This now equals, let's see, 42, 8 plus 42, right? 3 goes into 120, 40 times into 8, twice with 2/3 remainder, so this is 50 and 2/3. All right, lots of detail there, but this would be using our double Riemann sum in order to get through all of this. I know there's a lot. This is very tedious. Go through it nice and slow. See if you can't hash out all of the details here. I totally found a mistake. When I reduced the 6 and the 256, I only canceled out a 2 here. So that should be a 128 on top. We can fix this pretty quick. So 128 here, 128 here. 28 times 2 is 256. So we have 256 here. 128 times 3 is 360, and 24 is 394. This number's not going to matter when we take the limit here. And then minus 128. So I take the limit and we get still 8 at the beginning and 256 over 3 here. So that's now going to be 3 goes into 2480 times, and then 16 another 5 times over 80. Hold on. Make sure I'm not messing this up. It goes into 256. 8, 24 minus 16 is 5. And remainder 1. Oops. And that looks a little bit better. Okay. So obviously there's a lot here and it's easy to maybe miss something, have like a little number go missing or reduce incorrectly. What I really want to see as you're working through these problems is that you're using the summation correctly, that you understand that we're not taking the sum of the answer. So if I take the sum of I equals n minus 1 times n over 2 when I'm doing from I equals 0 to n minus 1, I don't want to see the I missing here. We don't want to think of a variable as a constant. We want to make sure that we understand when we're taking the sum with respect to I or the sum with respect to j, so that we understand what's constants, what are not constants, and have you pulling things out in the correct order here. That's the most important thing that we want to see. All right, so here's an example for you. Find the sum of x squared minus 2xy plus 3y dA for the region from 0, 1 in the x direction and 0 to 3 in the y direction, and do this using upper left corners. So upper left is going to be from, for my y values, we're going to do j equals 1 to m instead of j equals 0 to m minus 1. So it'll just be a slight adjustment there for you. See if you can hash that out. I will work through the solution with you in just a few moments. For now, you try, pause the video, and I will be back with you shortly. All right, we're back. I'm going to run through this pretty well. I took some shortcuts, but the main thing is that you're getting the same right answer, and even if you had some extra steps in between, are you getting some of the same places that I'm getting along the way? And can you make adjustments to get there if it's not exactly correct. So I'm looking for the double integral over the region from 0 to 1 in the x direction by 0 to 3 in the y direction of x squared minus 2xy plus 3y d capital A. Our delta x is going to be 1 over n. My x sub I equals 1 over n times I. My delta y equals 3 over m. My y sub j equals 3 over m times j. So I plug my x sub I and my y sub j in for x and y in this expression. The double integral is the limit as m comma n goes to infinity of the sum from I equals 0 to n minus 1, the sum from j equals 1 to m, and I'm doing this from 1 to m in the j direction because we want the upper left corners instead of the lower left corners now. And for x, we plug in 1 over ni, all of that squared, minus 2 parentheses 1 over n times I, close parentheses, open parentheses, 3 over m times j, close parentheses, plus 3, open parentheses, 3 over m times j, close parentheses, close big parentheses, times 1 over n times 3 over m. This equals the limit as m and n go to infinity of the sum of I equals 0 to n minus 1, and then big parentheses, the sum from j equals 1 to m of 3 over n cubed m times I squared, minus 18 over n squared m squared times I times j, plus 27 over m squared n times j. I did this by distributing the 1 over n and the 3 over m into each of the terms. Now, inside this sum, the first term is considered a constant. The second term, we have the j as the variable, and it's just j to the first, so this is going to become m times m plus 1 over 2 when we take its sum of j. Same thing for this other j. So we get equals the limit as m and n go to infinity of the sum from I equals 1 to n minus 1 of 3 over n cubed I squared, because the m's cancel, minus 9 over n squared m squared times I times m plus 1, because the 2 and the 18 reduce, plus 27 over m squared n times m plus 1 all over 2. So we then distribute this sum across to each of the terms. We get the limit as m and n go to infinity of 3 over n cubed times the sum from I equals 0 to n minus 1 of I squared, minus 9 over n squared m squared times m squared plus m all over 1 times the sum from I equals 0 to n minus 1 of I, plus the sum from I equals 0 to n minus 1 of 27 over m squared n times m squared plus m all over 2. This then equals the limit as m and n go to infinity of 3 over n cubed times parentheses n minus 1 times n times 2n minus 1 all over 6. The 3 and the 2 reduce to a 1 and a 2. Then we get minus 9 over n squared plus times m squared plus m all over m squared times parentheses n minus 1 close parentheses times n all over 2 plus 27 over 2 times m squared plus m all over m squared times 1 over n times n. The n's reduce here. This then equals the limit as m and n go to infinity of 2n cubed minus 3n squared plus n all over n cubed minus 9 halves times m squared plus m over m squared times n squared minus n over n squared plus 27 over 2 times m squared plus m over m squared. And when we take that limit, we get that this equals 2 minus 9 halves plus 27 over 2 equals 11. And again, I'm not hashing out every detail, and I want you to say, if you're not sure how I did something, how would you do it, and can you show that they are equivalent by using your algebra skills? All right? Let's move on. You've got another exercise now, exercise 13.2.1. Find the double integral over the region R equals from 0 to 2 in the x direction by 0 to 3 in the y direction of 3x minus 2xy d capital A using upper right corners. So now you'll use from I equals 0 to, I equals 1 to n, and j equals 1 to n. So j equals 1 to n is the upper, the right is the I equals 1 to n instead of 0 to n minus 1. And go ahead and do this. And I will come back and work through the solution with you in just a few moments. And we're back. So we have a delta x equaling 2 over n, x sub I equals 2 over n times I, delta y equals 3 over m, y sub j equals 3 over m times j. So our volume equals the double integral over the region from 0 to 2 in the x direction, 0 to 3 in the y direction of 3x minus 2xy d capital A. This equals the limit as m and n go to infinity of the sum from I equals 1 to n, j equals 1 to m. And that's again because we're using upper right corners now, of 6 over n times I minus 12 over mn times ij, all times 6 over mn, and that is from plugging in my x sub I and y sub j in for x and y respectively, and dA again is delta x times delta y to get our 6 over mn. I then go ahead and distribute the 6 over mn in to both terms inside here, and now I'm going to take the sum from j equals 1 to m of what we have inside here with respect to j. So this equals the limit as m and n go to infinity of the sum from I equals 1 to n of the sum from j equals 1 to m of 36 over mn squared times I minus 72 over m squared n squared times I times j. Now the first term, 36 over mn squared times I, is considered a constant. So the sum of that m times is just going to multiply it by m. The second one, the sum of j is m times m plus 1 over 2, and we're doing from j equals 1 to m. So this equals the limit as m and n go to infinity of the sum from I equals 1 to n of 36 over mn squared I times m. The m's will cancel. Minus 72 over m squared n squared I times m plus 1 over 2, and we take the sum of j from j equals 1 to m. This then, I'm going to reorganize just a hair. This equals the limit as m and n go to infinity of the sum from I equals 1 to n of 36 over n squared I minus 36 over n squared times m squared plus m all over m squared times I. So I move the I to the right, the 72 and the 2 reduced to a 36 over 1. And I distributed the m through to get m squared plus m on top here. This now equals the limit as m and n go to infinity of 36 over n squared times n plus 1 on top over 2 minus 36 over n squared times m squared plus m all over m squared times n parentheses n plus 1 close parentheses over 2, and that was from taking the sum of the I in both of the terms above. The sum of I from I equals 1 to n is n times n plus 1 over 2, so that happened both here and here, replacing the sum of I in both terms. I then went ahead and distributed the n across the n plus 1 in both of those, and rearranged a little bit. So this equals the limit as m and n go to infinity of 18 times n squared plus n over n squared minus 18 times m squared plus m over m squared times n squared plus n all over n squared. And so when we take the limit as m and n go to infinity, we can see that the n squared plus n over n squared is going to go to 1, the m squared plus m over m squared goes to 1, and the n squared plus n over n squared also goes to 1. Also, these 18s came from reducing the 36 and the 2. And so we get 18 minus 18 equals 0. What this is saying is that we have a positive volume on above the xy plane and a negative volume below the xy plane that are equivalent and cancel each other out in this case. All right. We're now going to look at essentially how we can apply this in a little bit more meaningful way now. When I say that, what I mean is if we have measurements that are giving us data points and we want to estimate some measurement that's a computation of those data points, then we're not going to have a continuous function that we can actually take a double integral. We're actually going to have to approximate things by just using the data given. So let's look at this in the following example. Example 13.2.4, a volume of sediment is being measured in a geological survey. The depth of the sediment is measured every 3 meters in both directions and is given in meters in the following table. Use upper left corners to approximate the volume of the sediment. So here we're not able to take a limit as the widths of the rectangles go to 0. Here we have the widths and lengths of each rectangle is 3. We see that delta x equals 3 and delta y equals 3, that there's no adjusting that. So here in the x direction, if we're at the 0, 0 coordinate, if I'm looking down at this, this has a depth of 0. So we move to right to the, in the y direction, we get a depth of 2, 4, 3, then 0 again. And if we moved with y as 0 in the x direction, we would get the depth is 0, 0, 1, 1, 0. So my y values are 0, 3, 6, 9, and 12. My x values are 0, 3, 6, 9, and 12 as well. And the depths, if we have x is 0, when y is 0, the depth is 0. When x is 0 and y is 3, the depth is 2. When x is 0, y is 6, the depth is 4. When x is 0, y is 9, the depth is 3. When x is 0 and y is 12, the depth is 0 again. Now we move to when x is 3. If y is 0, the depth is 0. If y is 3, the depth is 3. If y is 6, the depth is 5. If y is 9, the depth is 4. If y is 12, the depth is 1. Moving to x is 6, then if y is 0, the depth is 1. If y is 3, the depth is 4. If y is 6, the depth is 6. If y is 9, the depth is 5. If y is 12, the depth is 2. Now we go to x is 9. If y is 0, the depth is 1. If y is 3, the depth is 2. If y is 6, the depth is 4. If y is 9, the depth is 3. If y is 12, the depth is 1. Moving to x is 12, last row here. Then if y is 0, the depth is 0. If y is 3, the depth is 1. If y is 6, the depth is 3. If y is 9, the depth is 2. If y is 12, the depth is 1. So if we then think our x sub I is going to be starting at 0, and then the delta x is 3 times I, my y sub j is going to be 3 times j, because again y starts at 0. So the volume is approximately no limit now. We're going to take the sum from I equals, we're doing upper left, so I is my x's, we'll do 0 using the left ones, and to n minus 1, note we have 1, 2, 3, 4. So there's a total of 5 x values, but we're going to have 4 rectangles that we use, because there's an interval from 0 to 3, an interval from 3 to 6, an interval from 6 to 9, and an interval from 9 to 12, which makes 4 intervals for 5 given x values. So the first interval is from 0 to 3, the second interval is from 3 to 6, the third interval is from 6 to 9, and the fourth interval is from 9 to 12 in the x direction. We'll have a symmetrical same set of intervals in the y direction here, 4 of them. So I equals 0 to 3 makes a total of 4 intervals in the x direction, and then in the y direction, we're doing from j equals 1 to 3. We want of f of x sub I comma y sub j, and my delta x is 3, my delta y is 3. Now here we're not really able to use this summation because we don't have an expression for my z values, we have a table. So if we're using upper left corners, then my left corners are going to be when x is 0, 3, 6, and 9. My upper is going to be when y is 3, 6, 9, and 12. So we have a total of 16 separate rectangular solids that we're looking at. we have the first one. Instead of using a summation, I'm going to essentially just say the area of each, which is 9, actually let's use the delta, the change in area, is 9, and then we have the z values for when x is 0, we're on the left corners, and then y is 3, 6, 9, and 12, we get the z values of 2, 4, 3, and 0. And then when x is 3, we get, and y is 3, 6, 9, and 12, we get the z values of 3 plus 5 plus 4 plus 1. When x is 6 now, y is 3, 6, 9, and 12, we get 4 plus 6 plus 5 plus 2. And then when x is 9 and y is 3, 6, 9, and 12, we get 2 plus 4 plus 3 plus 1. Now really this is 16 different rectangular solids, so we take the area of the base of each and multiply it by each of the heights, but since the area of each base is the same, we've factored it out into the front so that I multiply once instead of multiplying 16 times and then adding. So I have 9 times 2 plus 4 is 6, plus 3 is 9, plus my second one is 8, 4 is 12, plus 1 is 13, and my third one 10, 15, 17, and my fourth row 2 plus 4 is 6, plus 3, I forgot my 1 here, 9, 10, and so here we add these up and I get 9 times 22, 32, 39, 49. 9 times 40 is 360, plus 81 is 441. And so now we have estimated our volume to be 441. Since this is a story problem, I want to write a conclusion and talk about my units here. So the volume of the sediment is about 441 cubic meters. Okay, now that we've done this example, we want to kind of break things up again, but using a midpoint rule. So instead of using lower left corners or upper right corners or lower right corners or something like that, if we have some, so this is my region R sub I comma j, instead of using one of the corners as we have been, we want to use the midpoint right here. So if this is x sub I and this is x sub I plus 1, and this is, well, I guess this is x sub I. I'll be specific how I write this. This is x sub I, y sub I, j. This is x sub I plus 1, y sub j. This is x sub I plus 1, comma, y sub j plus 1. And this is x sub I, comma, y sub j plus 1. Then this point here, we're going to call x sub I bar, comma, y sub j bar. And I'll get in, and well, I guess, so x sub I bar is going to be the average of x sub I plus x sub I plus 1 over 2. And y sub j bar is going to equal y sub j plus y sub j plus 1 over 2. And since the, well, let's see. Okay, so this one, the this is going to be y sub j plus 1/2 of delta y. And that is if we're making the change in y equal, so that from y sub j to y sub j plus 1 is delta y, then if I start at y sub j and add half of delta y, I will get to the halfway point between the y values. And similarly, this is going to be x sub I plus 1/2 delta x. And so we're going to see that here. Let me just read this. As seen in the previous examples and exercise, we can formulate our Riemann sum to calculate volume using lower left corners, lower right corners, and upper left corners or upper right corners of the rectangles. Since we are taking the limit as m and n go to infinity, it makes our rectangles infinitesimal, so the y values of the corners collapse on each other. Similarly, we may reformulate the Riemann sum again using the midpoints of the rectangles. So definition 13.3.1, given z equals f of x comma y, the volume between the surface and the xy plane over the region R equals a to b in the x direction and c to d in the y direction, where a to b is divided into n subintervals and c to d is divided into m subintervals, is given by the volume equals the double integral over the region of f of x comma y with respect to capital A, the area, equals a limit as m and n go to infinity of the sum from j equals 1 to m and I equals 1 to n of f of x sub I bar comma y sub j bar times delta x delta y, where x sub I bar is the midpoint between x sub I minus 1 and x sub I, and y sub j is the midpoint between y sub j minus 1 and y sub j. This method is known as the midpoint rule. So we're going to go ahead and have we're going to break up our x interval into equal parts, equal width subintervals, and our delta y is going to be the same across the y interval. So we're going to break up our y interval into equal width subintervals. And so our delta x is going to be b minus a over n, and our delta y is going to be d minus c over m. So x sub I bar is going to equal x naught plus x sub 1 over 2 plus delta x times I minus 1. So this gives us, if I is, so let's say we've got x naught to x1, then we've got x1 to x2, and we keep going all the way to x sub n minus 1 comma x sub n. Then the midpoint is going to be x naught plus 1/2 delta x. So if I is 1 rather, so my x sub 1 bar is the midpoint between x naught and x1. Let's put that right here. So if I plug in 1 for I get no delta x's, and I just get x naught plus x1 divided by 2, the average of those two. And for x sub 2 bar, this should be the average of x naught plus x1 over 2, the midpoint here, plus a single delta x, so that we move from here over by delta x to get to the midpoint of the next interval, and so on and so forth. So if I is 2, then we are going to add a single delta x to the midpoint of the first interval. If I is 3, we'll add 2 delta x's to the midpoint of the first interval, and so on and so forth. And then similarly for our y midpoints, we will have the average between y naught and y1 over 2 gives me the midpoint for the first y subinterval, and then we add delta y for each successive j value to get to the successive midpoints of each subinterval. So we're going to use this, and we're just going to do an approximation here. Doing the limits and all of that gets really long and tedious here, so we just want to do an approximation for the double integral over the region R equals 0 to 2 in the x direction, 0 to 3 in the y direction of 2x plus 3y squared, delta capital A, with n equals 4 and m equals 3. So if n equals 4, our subintervals in the x direction are going to be 0 to 1/2, 1/2 to 1, 1 to 3/2, and 3/2 to 2, so that we have 4 subintervals. In the y direction, we're cutting up 0 to 3 into 3 parts, so we have 0 to 1, 1 to 2, and 2 to 3. So we have x sub 1 bar equals 1/4, x sub 2 bar equals 3/4. And we see delta x is 1/2, and indeed 1/4 plus 1/2 equals 3/4. X sub 3 bar equals 5/4, and x sub 4 bar equals 7/4. And then my y sub 1 bar equals 1/2, y sub 2 bar equals 3/2, and y sub 3 bar equals 5/2. So we then are going to have all these rectangles. Note, well, let's real quick, I want to say delta x equals 1/2, delta y equals 1. So the double integral over our region of 2x plus 3y squared d capital A, this is approximately going to be, well, the z values of all the rectangles are going to be given by 2x plus 3y squared. And dA is the area of one of the rectangles, let's say. So delta A equals 1/2 times 1 equals 1/2. And then all the z values. So we're going to have, if I plug in, let me write this, f of x comma y equals 2x plus 3y squared. So we want to plug in f of x sub 1 bar comma y sub 1 bar. So that's going to be 2 times 1/4 plus 3 times 1/2 squared, which equals, oops, so 2/4 plus 3/4 is 5/4. It's just lagging here. There we go. So this is z sub 1 bar. Actually, no, this is z sub 1, 1. We also are going to then do this for f of x1 bar comma y2 bar, which is 2 times 1/4 plus 3 times 3/2 squared, and this equals 1/2 plus 27/4. Oops, I want to write this as 2/4 plus 27/4 is 29/4. I am going to leave that, and I'm going to do this for all 3 of the y values. So then we have f of x1 bar comma y3 bar is going to be 2/4 plus 3 times 25/4, 75, 79/4. And then we move on to x2 bar. Right, we want to do this for all pairs here, x1, y1, x1, y2, x1, y3, and then x2, y1, x2, y2, x2, y3. We see that we have a total of 12 rectangular solids that we're making, right, with all of these, 3 times 4. And so we need to get this for all of these. Now we want to speed this up a little bit, so I'm going to scroll. I want to just kind of get these down. So I've got f of x2 y1 equals, so I'm going to do this a little bit faster. This is 6 quarters plus 3 quarters, and then we'll have f of x2 y2 equals 6 quarters plus 27 quarters, because I'm kind of using what we already did here. F of x sub 2 y sub 3, the 6 quarters stays, and then we have 75 quarters over here. So now I've got 9/4 plus 33/4 plus 81/4. And then we do f sub x sub 3 bar, comma y sub 1 bar. For x sub 3, we've got 5/4 times 2 is 10/4 plus 3/4, and then the next one, x. So I'm just doing my pattern recognition to try and speed up my calculations here. 10/4 plus 27/4 is 37/4. F sub x3 bar y sub 3 bar is going to be 75 plus 10 is 85/4, and then we'll do this for f sub x sub 4 bar, y sub 1 bar. So x sub 4 is 7/4 times 2 is 14/4 plus 3/4. And so how did this zoom out a little bit? Let's see if I can fix this. There we go. And then we have f of x sub 4 y sub 2. This is going to be 6 plus 14 is 20/4. I'm just going to leave everything in fourths. F of x sub 4 y sub 3 is going to be 14 plus 75 is 89/4. So I'm going to put all these in now. I've got 13/4 plus 37/4 plus 65/4 plus 17/4 plus 20/4, oops, plus 89/4. And then we want to multiply these by delta A, which is 1/2. So this equals, let's see, all right, so we got 34 and 79 is 113/4. And then I've got 42, 123/4 plus 13 and 37, 50, and 65 is 115/4 plus 37 and 89. I hate adding 3 and 8. It's 110, 119, 126, 109 here, 119, 126, yeah. 126/4, all times 1/2. So that's 236, 336, 346, 351, 451, 471, 477 over 4 times 2 is 8. And we can just leave it just like that, or I can say, okay, 8 goes into 400, how many times? 50 times, and then 8 goes into 64 8 times, so 58. 59 will get us to 172, and then I've got 5/8 left over. And so here we're just using midpoints to approximate the total volume. And so our volume is approximated to be 59 5/8. Okay, last topic for the lesson, we want to talk about average values. So section 13.4, average value. Let's build up the idea of average value for the volume between the xy plane and a surface given by z equals f of x comma y on some given domain D. First, let's look at the classic computation for the average of some set of numbers given some set of y values, y1, y2, all the way up to yn. Then the average value is equal to 1 over n times the sum of from I equals 1 to n of the y sub I. Right? That's just y sub 1 plus y sub 2 plus y sub 3 all the way up to plus y sub n all over the number of objects, right? That's our classic definition for the average value. If we rearrange this equation, we get n times the average value equals the sum of all these elements, right? So if I just multiply the n to the other side, we get that the total sum equals the average times the number of objects, which is a really nice thing to have, to think about it in this kind of backwards way. So writing it in this way is to highlight that the average value is a height y value such that multiplying it by the total number of y values gives us the same as the total of all the y values, right? If I add up all the y values, then if I will get that same total by taking the average value and multiplying it by the number of values. Because we want to extend the average value definition in this manner. So this idea can then be extended that the average value of a continuous function over some interval a to b gives us that the total width of the interval b minus a times the average value equals the integral from a to b of y of x dx. That is the total area under the curve right? This area equals the integral from a, if this is a and this is b, the integral from a to b of y of x dx, where this is y of x is this line here. So that's just all of these heights added together and with infinitesimal widths. That is our area. So we are taking the average of those by saying what's the average height, and the average height is going to be a height where the width times this height is the same as the area under the curve. See how that's a connection to what we were doing here? The total y values divided by the number of them. If I move the n over, then the n is the number of things times the average gives us the total sum. And instead of the number of things, we now have a width. So this is analogous to what we were doing above. We can then say that the average value, and this is what you actually see in our second term calculus, is 1 over b minus a times the integral from a to b of y of x dx. So we can again see that the average y value is the average height, so that the width times this y average gives us the area under the curve. We now extend this to the idea of the average z value of some function z equals f of xy over some domain D, so that the area of the domain, so before we had the width of our interval, now we have the area of the domain times the z average value is going to give us the volume between the xy plane and the z value itself. So the double integral over the domain of f of x comma y d capital A. So we can compute the average z value via the formula. The average z value, let me draw a picture of this. Let's finish reading. The average z value equals 1 over the area of the domain times the double integral over the domain of f of x comma y d capital A. So we've got some surface here over some domain. Let's see. So our domain, say, is circular, but the z values are changing across this. Then, so say we've got x and my y directions here. Here's my y-axis, and this is parallel to the y-axis. Here's my x-axis. Here's my z. Then the z average is some height where if I multiplied the area of this domain, so this is D, is this space in here. If I take that area and multiply it by this height, then I'm essentially doing a prism volume, not prison, prism volume. So this area times the height of this prism. If we had just a flat top, then we want the area of this prism to equal the area, or I'm sorry, the volume of this prism to be the volume under this curve, right? So we're choosing the z average to be the height where that works out. So let's do that using example 13.4.1, where we're actually doing contour maps, and we're going to use some midpoints to approximate the average value here. Example 13.4.1. The contour map shows the temperature in degrees Fahrenheit at 4 p.m. on February 26, 2007 in Colorado. The state measures 388 miles west to east. So we're going to say that this is my 0. This is at 388. And 276 miles south to north. So we'll say this is the 0 in the y direction, and this is 276 in the y direction. Use the midpoint rule with m equals n equals 4 to estimate the average temperature in Colorado at that time. So what we want to do here is I'm going to start by dividing it down the middle, and I'm doing a pretty rough estimation here. So I want to divide the x direction into 4. I'm cutting it here, cutting it here. And we're cutting it about here, so that I've cut it into fourths in the x direction, so that n is 4. And then I'm going to cut it in the y direction, in half, and then in half again, so that I've divided it into fourths. And then we want to look at the midpoints, or approximate midpoints, of each of these. So our map here is showing temperatures, and we can see that the redder the color, the hotter the temperature, the bluer the color, the colder the temperature. Yellow to green is kind of in the middle. And we want to kind of get an idea. Whoops, that's not very middle-ish. It's about, sure, there. So we want to know what the z values are for each of these to be the heights. We know that the width here, 388 divided by 4. 388 divided by 4. This equals 97. So this is at 97. And then 194. And then at 291. And then 388. And 276 divided by 4 is 69. So we've got 69, 138, 207, and 69 again would give me 76. Great. So we can see that our delta A is 69 times 97, which equals 6,693. So my volume over the state of Colorado, which is really essentially all the temperatures everywhere added together. So this is my temperature, x and y, dA. This is approximately all of these midpoint temperatures added up. and then multiplied by delta A. So what do we got here? If we're on, I want to just, so 28's like the border of the teal and the green. Looks like 32 is right here on this edge. You have something that's out in the middle of the green that's labeled. We have 28 here, 30. Okay, 28 is on the edge of the teal and the green. And then 32 is on the edge of the green and the lighter green to yellow color. So that would say that we're probably about 30 at this point, 32 at this point. Here in this more yellow but slightly green color, that over here says that it looks like about 44 is in the yellow, 44 is on the border of the yellow to that green. If I'm in the middle of that green, it looks like I'm probably about 42. Here we're on that border from green to light, or like the green to greenish yellow, so that's 32. Here if we're in this light blue, we're at like 26, between 28 and 24 here. And so here I'm kind of like on the border, a little bit more green, so that's maybe 27. And we're doing approximations here. Obviously these dots aren't exactly in the center because I'm not using a nice ruler and straight edge here. A little bit tough on a Wacom tablet. So if I want the border of the purple to the green, that's 20. And then the border from the green to the light green, that's, I guess, 24 right there. And then this color is like 42 in here, 42, 42. The yellow is, I feel like this number's wrong, 44 here, 48 there, so the yellow is 46. We're in the yellow. 56 here. If we're in the red, we're probably like 58 because it keeps going up by 4s, right, between these contour lines. This is probably 58. Here we're on this contour line, so 52. Here, 44. 48 and 44. So if I take all these and take this and multiply it by the area, that gives me this kind of total temperature over this region, which doesn't have a whole lot of sense, but when we then divide it by the total area of this region, then we're going to get the average temperature over this region, and that makes a bit, that we can wrap our heads around a little bit better. So let's take these. We've got 30. I'm going to need to have a little bit more room here. 30 plus 32 plus 42 plus 32 plus 24, 20, 27. 26, 42 plus 46 plus 58 plus 52 plus 42 plus 44 plus 48 plus 44. And then we multiply those by our delta A. So we got 62, 104, 136. I'm going to add these 4 at a time. 44, 64, 71, 97, 88, 138, 146, 148, 198, 86, 126, 134, 174, 178, and my delta A is 6,693. This equals 136, and 236 minus 3 is 233. 233 plus 200 is 433, minus 2 is 431, 531, 601, 609. And let's not multiply these together because it's not really what we're looking for. What we're looking for is the average temperature, which is going to be 1 divided by the total area, so the area of Colorado, and times this integral here, the double integral over the state of Colorado of the temperature function with respect to the area. And this then, 1 over the area is 276 times 388. And note that this, so this then, I'm going to kind of just, there's a way that I can simplify this pretty quickly. 6693. Note that this is 4 times 69, and this is 4 times 97. And this is 69 times 97 right here. So this is 4 times 69 times 4 times 97. Let's have a way of canceling things real quick. 609 times 69 times 97. So we can cancel, 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 cancel. This equals 1/16 times 609, which is approximately 38.06. No, that's exactly, but oops. 8.0625. And so we've got a story problem here, so we want to write a conclusion and say that the average temperature in Colorado on February 26th, 2007 was about, because this is very much an approximation, we only did 16 points here. If we had, 1,000 data points, we could do this much more accurately. But that would still be an approximation. But this was about 38 point, we'll just say 1 degrees Fahrenheit, because, yeah, this was scrolling up here, measured in Fahrenheit degrees. So, and this was at a specific time. So we want to make note of that. This is not over the entire day. This was at a specific time. 2007 at 4 p.m. was about 38.1 degrees Fahrenheit. All right. That's what we have for you in this lesson. Thanks so much for watching, and I will talk to you in the next lesson.